A topic today is incorporating AI into your Industry 4.0 transformation. And we're taking a control perspective. So what we would first like you to do here, thank you all for telling us where you're coming from, great international group. Could you also in the chat let us know what brought you here today? Why did you sign up for this webinar, and what would you really like to get out of it? So if you can put that into the chat, that would be great. Really helps us connect better with your interests. So let me introduce as well John Carrier. He is a senior lecturer at the MIT Sloan School of Management in our System Dynamics group. John has great experience as a practitioner working in industrial settings for probably close to 30 years now. He has seen digital transformation come into industrial settings, quite knowledgeable about that, as he will tell you. And as we said in the title, he is a control systems engineer, so he brings a particular perspective there. John is active in executive education with us, and he also teaches in MIT's Leaders for Global Operations program, which is our unique dual MBA and engineering master's program, very select program. I mentioned the Industry 4.0 program. Our next session there is on October 31st, November 1st. It is on the MIT campus. We'll come back to that at the end of the session here. I'd like to talk a little bit about what we're going to cover. What we're going to cover in today's webinar, really three main topics here: how to match the technology to system performance and avoid overinvestment. Second, using the fundamental control principles to guide your organizational transformation. And third, understanding the vital role of the front line in the transformation and the leadership qualities that are required to create a system that works for everyone. You know, we talk a lot about technology. There are people in organizations as well, and it's essential that we've got people and technology processes well aligned. Last thing I'll say, and then I'll turn it over to John, is we welcome questions and comments along the way. If you can do that through the Q&A tab in Zoom, we'll be monitoring, and we'll look to bring as many of your questions into this as possible. So John, great as always to work with you. The floor is yours.
Great. Thank you, Eric. And thanks everyone for joining today. And just a little bit about me. I was born and raised in Detroit, so kind of absorbed that auto industry experience and decided I was not going into the auto industry. So I went into chemical engineering and control systems. And when I came to MIT in 1990, we were actually at the second or third wave of artificial intelligence. It was a really hot topic. And after about 6 months, I thought I was going to incorporate artificial intelligence into control systems and realized if I did that, I'd never graduate. And so I really did a more traditional time series based control types approaches. And what's interesting about today is we're seeing some of the leaders in artificial intelligence actually bringing in many of these concepts that came from the 60s and 70s from control systems. And what's really behind all this, and I realize, Eric, there's we put AI in the title of this presentation for two reasons. One, so you'd see it and attend, but second, to also explain its actual role. And when you're building when you want to control anything, be it a chemical plant, be it an entire organization, what control theory told us from the 60s to the 80s is every control system has a model. And the quality of that model determines how well you can control that system. That breaks us into two pieces. One, build better models, which we're going to touch on that in terms of Industry 4.0, because first we need good sensors, right? Have good models, because we need to measure what we're doing. And then second, we need good algorithms. And machine learning has brought a lot of that with us. But this isn't just an academic exercise. We're running businesses here. So we need to keep healthy cash flow both to satisfy all our stakeholders today, but to be sustainable in the model in the future. So it turns out that simplifying your system is actually a huge, generally untapped initial approach when you go to transfer into Industry 4.0. And we're going to look at that. And what we're going to end with is a discussion of how I've put together like an MIT really two-gap, two-phase model for when you adopt Industry 4.0. And it's going to do two things: explain why many current Industry 4.0 launches fail, and then two, how you get over that and be successful. Because one of the things I really want to keep in mind is the most valuable thing in any system is you're trying to control time. And we really appreciate the fact that you are here to spend an hour with us today. If you don't adopt the new technologies, your company will fade out. But many companies that do adopt new technologies suffer because they overinvest in the wrong technology, which can also be very painful and lead to bankruptcy or acquisition. And we're going to discuss that there really is a better way. So let me tell you about what the current movement in artificial intelligence is with respect to manufacturing and industries. Here we have Andrew Ng. So he's one of the luminaries in artificial intelligence for at least the past 15 or 20 years and has done some spectacular work on visual recognition. But I just want to point out this key article that he wrote. This is only about 2 years old in IEEE Spectrum, Unbig in AI. So what does that actually mean? It means that we're moving away from that data's the new oil and throw every bit of data to when you select your data set carefully. And what I've learned from 30 plus years of control system development, select your data based on your system and what you're trying to accomplish. That's why my background here in system dynamics here at MIT is so important. And it's also why it's so important that you spend some time out on the factory floor with the people doing the work or the operations center before you start introducing this new type of technology. Okay. And just to give you an idea of where this has been advancing. So on the left, Andrew Ng's company, Landing AI, some very good work on model training. So basically high-speed visual recognition of defects, which is of fundamental importance in operations and manufacturing. And directly from that website, notice the prerequisite. If you want to use the full value of one of these large models for visual recognition, they're recommending 100,000 unlabeled images minimum if you choose to use unsupervised learning. And for those of you who study AI, I took a class with Marvin Minsky in 1992. And I remember back then he said, in order to train a neural net to recognize good from bad, you need at least 40,000 photographs. And Eric, that was back in the day when photographs were Polaroids. So I just could not imagine it. Still, even though we can have 100,000 images, that's a lot for training. And however, what are some of the things we can do about that? And I want to show you some work that some of our students did here at MIT through our LGO program. It's if we understand the system, we can actually, in certain instances, create data without actually going through the expense of creating it naturally. This is called synthetic data. And this is a spectacular example. You'll notice that's a medical syringe on the left. It's made at high speed. And any type of defect could be disastrous. But in order to get enough defective parts, I mean, they run at 99% effectiveness now, or higher. So to collect each and every defect and run all those to train a neural net is almost impossible. So what our student did was actually create representative defective images by basically using things like Photoshop and video augmentation. And you'll notice here on the left, right at the top, you'll see that if you have too large of a bubble in your syringe, that means you're giving the wrong dose. That picture on the right image was made synthetically, and that makes training these neural nets not only very inexpensive, but also practical. And I just want to end on this slide is they actually tested this at the under high speed photography of these syringes. And you'll notice with a different defect, it had a small nick in the plunger. you'll notice in the lower right-hand corner, notice that with synthetic training, it immediately spots that defect, which was trained on synthetically, versus the control, which is the colored picture above it. So if we actually stop and think about our system and what we're trying to accomplish, we can greatly reduce the amount of energy and effort we use to train some of these models, yet still not lose the quality and speed that we need in operations and manufacturing. So just a concept Key want to bring across. And Eric, I know you always have good thoughts on these. Anything that jumps out to you or thoughts from our audience at this point?
I think not from our participants at yet on this, although I would encourage you all to send in any comments or questions that you have about this at this particular point in time.
Fantastic, Eric. So now we've looked at sort of basically, you know, all these neural nets, especially around video recognition, but this also holds for robotics. So on the left, you'll see that's Rodney Brooks, who's been working in artificial intelligence and robotics for about 40 years now. And this quote was less than 2 months old. Is he really thinks that people are vastly overestimating the value of Gen AI. And I just want to point a little bit about where he's been extremely successful. On the lower right-hand corner, you'll see that is Genghis. So that was Rodney Brooks's pioneering work on how to take the most simple components and with some simple feedback loops is actually build a robot that can actually train and actually, in this case, walk by itself, right? Which was an amazing accomplishment. As each that robot actually trains itself with little small models. And you'll also notice, look at the parts it was made out of. The motors are actually servo motors from standard radio control airplanes. So as we start to move and understand the technologies of AI and for Industry 4.0, the companies that I see are being successful is how to buy the least technology to achieve the greatest results. And this has actually moved on to robotics. Now robotics is one of those subjects that just gets a great deal of excitement about it. But when you look commercially, it hasn't been all that successful compared to some other startups. For instance, Boston Dynamics, which is a 26-year-old company, was acquired by Google. Now it's owned by Hyundai. And it's somewhat struggled to find proper use within manufacturing and industry. And on the left, we even see Rodney Brooks's most previous company, which built the Sawyer robot, which many of us have seen at trade shows, exhibits. And in 2018, that company went defunct and was purchased by another company. But let's see what Rodney Brooks is working on right now. This is from 2024, and this robot essentially is, quote unquote, intelligently brings supplies to and from either your assembly line or to and from your warehouse. But notice how simple and specific that robot is compared to the general types of robots that were being built, say, 5 or 10 years ago. And this simplification of the technology so that it's both practical and adoptable is really where the industry is going. We saw it with respect to Andrew Ng's work, and now in visual recognition and reinforcement learning, and now we're actually seeing it with factory floor robotics with Rodney Brooks's work. And one of the key reasons that we really focus on through the course is success is fantastic. But we really want to make sure that as you work through your investment or into your company, that you avoid major failure that could be catastrophic to your project and your career. And most recently, we've been given this one by McDonald's. They had a multi-year investment with IBM, and they literally shut down this entire program for artificially intelligently driven drive-up menus. And the reason, the reported accuracy of transcription was only about 85%, right? Which, as you can think of, is catastrophic for any sort of line or queuing management in the service industry. However, other companies have reported greater success. For instance, Popeyes in the UK had an accuracy of 97%. And if we stop and think about what's driving this accuracy, it's probably due to the fact that the companies looking for success did not fall in love with the technology and focused on building something that worked. So with that, I had the opportunity to have some discussions with several industry thought leaders who are investing in both artificial intelligence and large data for their companies, and are actually establishing transformation offices for these programs. And one of the most interesting discussions I had with one is the company was looking at these large language models, and his response was, why are we looking at LLMs when we only offer 5 products? And of those 5 products, there's only 4 or 5 issues that cause 80% of all our service problems. So if we don't scope the system problem down to specifics, we're going to actually introduce all these additional failure modes that we didn't need to. And we actually have some data on this. This is data related to how accurate a large language model is compared to essentially how many model parameters it has. And if you'll notice, comparing 3 of these large language models, you'll notice the one that's the highest accuracy, 73%, which is 3x the other 2, uses a less than 10% of the parameters, right? And if you stop and think why that is, it's because I like to think of it as when you take a multiple choice test. If they give you A, B, C, and D, Eric, there's no reason to choose G, H, I, or J, right? So if you bring in system knowledge, context, situational awareness, the quality is going to go up, the cost to construct it is going to go down, and the buy-in is going to be tremendous. And instead of a long, painful, drawn-out experience as McDonald's has, you'll have a much shorter, successful experience when you go to implement the technology. Okay, third, we talked about artificial intelligence, and in the title, we stress it's really a control problem. So I wanted to show you some correspondence from Jan LeCun, who's the chief AI scientist at Meta. And I won't go through all the details in his text, but you'll notice what he's talking about is what is a world model. And if you read through that world model about first you make an observation about the existing states, which is X, you estimate the state of the world. I usually use Y or from the control industry. And then we have an action variable. That is generally the model predictive control framework that was developed sometime in the mid-'80s. And it was actually one of the key developers of that, and Eric will know this, was my advisor's first student, Manfred Merari. And although this is well known in control system theory, particularly in chemical plants or aerospace, where you're basically trying to do trajectory guidance, autonomous vehicles, it's actually used in every organization that does some sort of forecasting or planning or strategic roadmap. And essentially, the basis for model predictive control is you're always looking towards the future. So the red line basically shows this is the trajectory we would like our organization to follow, right? And in order to follow that trajectory, we have certain actions we can take. So the trajectory might be the adoption of a new product or service, right? And the projection variable is revenue, right? Over a 3 to 5 year horizon. And we also have control variables such as marketing, advertising, trade shows, demos. And those are our control steps, which is shown in green. And in the that looks like a burnt umber color, but let's call it brown. That's what actually happens. And what we're actually trying to do is select the right control options, which is the green steps, so that we can push what's actually occurring from our measured output and make it correspond to the desired trajectory. In order to do that, we need three things. We need a system, right? And first, before we even start to invest in technology, let's make sure we have one system that actually produces our product or service. That's where during our course, we're going to touch on this concept of hidden factories, because the number one problem I see when I help companies try to adopt the new technologies is they help our system. And I'm like, really? You really don't have one system. You really have 4 or 5 systems, 3 or 4 that are hidden, right? That you use to expedite actions. That unless we actually straighten that out and understand it, we can't build a system around it. The second is we need some type of model, right? And fortunately, we're in this era where the mathematical models we'd like to use are not only fairly well understood, they're also widely available, and we have the computational power to do it. The last is data. And one of the most fortunate things of where we are in Industry 4.0 is in the last 20 plus years, the cost and quality of sensors has dropped 3 to 4 orders of magnitude. So what would have cost me 15 or 20 years to put in a real-time vibration sensor, several $1,000s, and I'd have to wait 4 weeks to get a control engineer to put it in for us. And then we would probably spend a week or 2 tuning it. You could do that now in minutes because you can basically buy wireless industrial quality sensors for vibration for under $500. However, and that also extends to infrared cameras, high-speed video, pressure, temperature, torque, stress, strain, you name it. The challenge is not to buy too much of those sensors, and in order to know where to put them, you need to be a control engineer, because the reason you're buying a sensor is because you're trying to implement a controlled feedback loop. And one example from a previous company I worked with is I came in, they just adopted a new, they had an Industry 4.0 launch, put in a new platform, and over the last 6 months, they'd installed 300 sensors. So my question was, so what are the sensors telling us? And the answer goes, well, we haven't had time to look at the data yet. I said, okay. And I go, I'm going to make a prediction. Let's check right now, and 20% of those sensors aren't working. It was 18%. So they were a little better than I thought. And then second, I said, why didn't we just put in 30 sensors at first, right? Because in any factory or facility, the top 30 pieces of equipment correspond to 80 or 90% of your problems. So then there was kind of a hush, and like, well, we never thought about that because this was supposed to be a big initiative. Now, if you want the big initiative and you want to invest up front because that's what the organization wants, that's fine. But if you want to implement this in a way that minimizes risk to your operations, your system, puts as minimal stress on your frontline staff, and also provides you with early results so you can justify what you've done and accelerate the program, you really want to be thinking about purchasing the technology in the context of new feedback control loops rather than some stamp that we're Industry 4.0 enabled. Okay. And I just like to conclude this part. This is work that comes from Donella Meadows. She was a research scientist in the system dynamics group at MIT. And she asked herself this really important question. If we actually wanted to change or intervene in a system and make massive improvements, she came up with 12 leverage points. And we'll share this slide with you, obviously, at the end. But she listed them from least effective to most effective. And I just wanted to point out 2 here. Number 8, the strength and quality of your negative feedback loops. This is something by using Industry 4.0 to improve those can really drive rapid performance. And we have several examples we'll go through in the course. But I also want to focus today is on number 2, the mindset or paradigm on how the system's built. So what does that mean? It means, what do we, as leaders and technologists, actually think the transformation should look like. And if we're coming from an era that we're going to just drop in new technology into an existing system, I think like McDonald's, that will be generally a recipe for failure. If we break it into two parts, first, we store our system back to health using certain technologies, particularly focused on observability, which we'll get to a minute. That will produce both early results. It will build strong engagement with your front line. And second, it'll give you the information for when you go, if you need to adopt more sophisticated technology. So we're through this process, we're always increasing productivity and we're always reducing risk, although it might not be the shiniest path to take. And with that, we are introduce many control concepts during the course. And in particular, I look at 7 key control system concepts you really want to consider at the start when you start on your Industry 4.0 journey. But I just wanted to, for the purpose of this discussion, just focus on one. And whenever you're looking at a system, and remember, organizations are living systems. They're very much like natural systems. So stepping back and learning from nature can actually be a very valuable effort when we go to do our transformation. And it keeps us away from that very dangerous, what's the ROI remark, which I find actually kills more good projects than it helps. So let's actually look at the concept of observability from nature, and then we're going to actually look at it from an actual organization, which here is a chemical facility. So when you think about observability and you think about nature, any animal has to do basically doing 2 things. They either need to be seen, right, for obvious reasons, or they want not to be seen. And most of the time, they actually don't want to be seen. But when something needs to be observable, there's no better example than the peacock, right? And there's several uses for that huge plumage. You'll notice all those little eyes. It actually can be useful to defend itself because it confuses a predator because it doesn't know where it's being seen. So sometimes observability is really important. Most times, we don't want things to be observable. And this is an incident where a peacock escaped from the Franklin Park Zoo here in Boston, Eric, and you can see the Boston Police Department. Noticed he's carefully folded his wings, right? And the reason why is if everything's observable in the system, it will become overloaded. Okay, now that is a general example from nature. I want to now take you to something specific as an industrial example, and I want to show you what happens when you lose observability when you really need it. On the left, that is the Chemical Safety Board's simulation of the Texas City refinery explosion. And the unfortunate incident was in 2005 at the Texas City refinery in Texas City, Texas. They overflowed a distillation column. And as a chemical engineer and someone who's worked in refineries for at least 5 to 6 years, the one thing you never want to do is overflow a distillation column. So there are many ways to deal with that. Is first, you have a drum that feeds the distillation column. It's at the bottom, and there's a level measurement. And at Texas City, that measured up to 9 feet. And it turns out if you overfilled the drum, it would saturate at 10 feet. And as you kept filling the drum, the sensor actually always read 10 feet. So if someone did not, if there was missing expertise in the control room, which is actually what happened, no one realized that they were actually overfilling this tank, and they lost a drum measurement. That was the one sensor that was working. There were also 2 other drum sensors that were on maintenance backlog. Okay, so that one failed. However, that's just the drum. Now we have a 150-foot column, right? And so there's alarms in the column as well. It's got what's called a high alarm. High alarm means the level's high, and it's so high that we need to basically shut down immediately. That alarm wasn't working, right? And so there was at least 2 losses of visibility. Now, here's why it's so important. The system, if it has a problem, it will keep amplifying its voice until it makes itself observable. And that's exactly what happened. And the first observability in this plant was unfortunately when the plume of heated hydrocarbon basically shot out the top of this column. And by that time, there was insufficient time to control or act, right? And it unfortunately led to 15 fatalities. Okay, so what does this have to do with some of the more modern tools that we have from Industry 4.0? I'd like to focus on 2. One is better, lower cost sensors that actually are low cost to maintain, are easily replaced, and can also indicate when they failed. And second, along with that, are mathematical models. You can basically call those digital twins at this point, but basically, 30 years ago, when you built a distillation column, you ran a mathematical model of it, or that's what I did. Today, you can run that design algorithm during operations. So if you're collecting certain vibration and thermocouple data, flow data, and you actually bring that into your real-time model, which let's call it a digital twin, since that's what's currently used, you can at least detect that something's gone wrong. And if we detect that something's gone wrong, we can then make this problem observable to the right people on the plant, right? And so I think probably the number one use case for Industry 4.0, particularly in the industries I work in, are safety. However, if you made this system more safe, since you understand it better, it's also going to be more productive and produce a higher quality product. So we are actually in a golden age for making small investments in large capital assets and creating tremendous results if we can break the mindset of this massive new investment in technology. Okay. And just where I'd like to really close out is first, again, thanks for your time. And what I'd love to do in just a moment, we're going to open this up to questions. But what we're really targeted here is giving you an opportunity to step back and think before we start taking for granted that we need to make this jump to Industry 4.0 or incorporating AI without specifically targeting the problem. So what we generally do is we have our spend 2 days here in Kendall Square. We go through some key concepts in system dynamics. That tells you what needs to be fixed. I think the biggest problem I see is we spend time on technology on the entire plant when we really only need to focus on 5% of it. That takes us to this concept of a hidden factory. The concept was developed here at MIT back in the early 60s. And with this new observability brought to us by Industry 4.0, the opportunity to identify and eliminate these hidden factories is unprecedented. And it produces an almost instantaneous positive cash flow and return on investment. So it's a fantastic place to start. We've also incorporated the fact that when you look at how information flows, we certainly know on the plant floor, it's by where we've got the wiring, what we've connected and how it runs to the computer. But information flow is also controlled by the organization and its culture. So if we're actually looking for a digital transformation, we actually have to take into account organizational culture right up front. We'll also look at some industrial use cases to draw analogies that you can take back to your facility or plant at Monday morning and give you some time to develop your own playbook. And of course, the greatest value is you get time to spend with some of your other colleagues from different industries thinking about similar problems and how we can get off to a better start. And obviously, since we're in Kendall Square and on MIT, we often get the opportunity to visit some laboratories. This is the Fred Laboratory on MIT campus, where it's a pretty advanced student laboratory doing additive manufacturing all the way from design to product. So those are some of the things we encourage, and we certainly would like to help you think through how you go through a transformation and how you can basically change the risk reward for yourself, for your company, and for your colleagues. And I just like to close on a model that I've worked on. This is a framework we've been using for the past couple of years. And I think the number one reason why these transformations either fail or fall below their time frames and investment marks is because they try to make the jump from current state to the vision state in one jump. And what I've really learned is you really want to do it in two steps, because unless you take out the old ways of doing things in the system, when you put in the new technology, you're just allowing the system to behave in more than one way. And that actually could make things worse. So the first step from going from current state to phase one is to first start thinking, how do we remove things in our system that don't belong there, that have accumulated due to all this lack of observability we've had for 20 years? So we want to remove variation in the ways we work, the ghosts of old technology, poor preparation, and chronic defects. Now, there is some technology we can add during that phase. Most likely, we're going to add some simple sensors and feedback loops. We'll probably establish a fundamental cloud platform for sharing data. And in fact, 80% of the time, I find the data we need for the next 6 to 12 months, we've been collecting for years. It was just either sitting on a machine, on the factory floor, or on somebody's laptop, and it was never analyzed. And this is particularly true for timestamp data, which is basically ubiquitous in its collection, but it's often buried somewhere in the facility. So just finding what data you have and analyzing that will help get you through phase one. Once we get through that, we can start thinking about, automation, maybe thinking about some augmented reality. And then once we get to phase two, now we're in good shape. We've already generated some positive cash flow benefits. We've achieved some victories in the factory floor. We've made the work easier to do. We've improved productivity, and we've reduced risk. And now we can better invest our technology by focusing on the parts of the system we want to do. So that's really this two-gap model we want to work on. And you'll also notice it counterbalances this relationship between the company and technology vendors. Now, one, you need technology vendors to make this journey. It's not possible without it, right? However, as vendors and your organizations work together, you really want to establish this longer sustainable path, right? And in the long run, it produces much more stable cash flows, and it's actually better for both the companies and for the vendors. And we found that to be a very useful model. And with that, Eric, I'd just like to, take some time and maybe we have some questions or thoughts or observations from our audience.
We do. Thanks, John. We've got a couple of questions about topics that were discussed earlier, synthetic data and LLMs, but I'd actually like to start with a question in the middle here from Inaki, because it relates to what you've just been discussing about how you go about doing these things. Inaki's question is about changing the mindset in industry. Should it be done using a bottom-up approach, i.e. successful case studies that can be replicated, or a top-down vision, i.e. from a global strategy from the board?
Here's my answer, both, right? But I want to address that very carefully. So, by the way, I am naturally a bottoms-up thinker. That's how I do things. And I'm really a doubting Thomas. So like when someone presents a big vision, I've always been this way. I don't know, I need something concrete that we can fix. So I've become very good at the bottoms-up approach. And what I think I also want to bring in is what I've really learned is the operators and people on the floor really understand that. And second, if you work with them, they will adopt what works for them. So if you start with a bottoms-up approach, you're going to get nearly immediate buy. All these things that they worry about at the top, buy-in from the front line. De-risking the technology, minimizing it, maximizing that investment produces a return. You're going to deal with all those things. However, you also need to start from the top. And this is something I didn't learn till the last 5 years is when I go and we start working with the companies. I will say in the top is yes, we have to have a vision of where we're going in 5 to 10 years, but I'm going to go work with the team on the floor, and we're going to produce you a positive result within 60 days. That's going to, like I said, be a positive on every metric. Now, how do we do that? One, we look for hidden factories, and two, we have the freedom to scope it down. When senior leadership sees this new type of approach, and they see you're actually the front lines actually working together to reduce risk and deal with those problems, and provide them with the right information so now they can scale it. Now we've pushed the problem in between the front line and leadership, so it can't get away. So in mathematics, that's called the squeeze theorem. So I hope that was helpful. I'd say 80% start with the top down, but I would start with both.
Great. Related question to this, about the two gap model that you just showed here. And I might, the question, I'll read the question and then I maybe just give a little bit of framing on how to think about it. Question was, how long should phase one and phase two take for a successful transition? I might slightly reframe this with permission from the questioner. How would you know if you were making how do you know when you're making progress, right? As one could imagine, there could be a lot of variation depending on what kind of processes you kind of fix, but how do you know when you're making progress through these?
So that's a great direction. It actually gets back to, I work for a lot of financially troubled companies that within 3 months without cash flow will go out of business. They're manufacturing. And that really focuses your attention. Number one, customer on-time delivery. Anything that touches that, too. And two, we don't send defects to customers. So a customer on-time delivery and quality. And you know what's funny? When you actually reduce customer on-time delivery, a whole bunch of scheduling problems go away, right? So that's what I would focus on first. And it's amazing. A colleague of mine, a company we've just been working on, and they actually do advanced wiring junction boxes for military and outside applications. We basically turned their cash flow around from -2 million to 1 million in about 3.5 months, right? It could have been faster if we were on site. However, now we're starting to actually bring in technology. Oh, and by the way, their quality defects went from 80%. Yeah, they were at 80%, had to be rechecked down to under 2%. And lead time went from 9 weeks to 4, because it was basically being run like a job shop, and there was no continuous improvement in there for 10 years. Now we're starting to bring in technology, particularly in now when an engineer creates a drawing, it goes to the factory floor immediately. They can get it, have access to it. So if we sell products with more variation, the system can keep up with it. So I would say the phase one can take anywhere from 3 to 18 months. Phase two is probably 24 to 36, but you can overlap the phase two over the phase one. But back to your question is, if we work on things like customer on time delivery and quality, the cash flows, lead times, and employee morale usually straighten themselves out.
Great. John, thanks. I mentioned earlier we had a couple of questions about where we had an observation from one of our participants about synthetic data, which may not always work in a real world case. And a related question, could you talk a bit about how Gen AI is used to create synthetic data or the current trends that you see on that topic? Thank you. So it's kind of it's an observation and a question combined in there, but just great to get your perspective on that.
So I'd like to take the first question. Now, remember, I come out of time series, like, data points on a graph, time, temperature, pressure, vibration, etc., concentrations. So when I heard about synthetic data, to me, that means you're just making up data and you're double counting from a statistics standpoint. So in general, if you're actually training a mathematical model, like an ARIMA model or RMAX or those kind of classic control models with fittable parameters that are finite, synthetic data is often double counting. So I would be extremely careful of, like, when you're taking neural nets and you're throwing in uh, multiple synthetic data to build a model of it, because you're actually weighting the model uh, based on your selection of what you see, and that's obviously going to bias what's going to happen. When you start looking at things like where I'm trying to recognize defects, right? Then you can start to see, so like if you'll notice on that syringe, one of the defects they have is on a rubber stopper. And so if you actually get a real defect in the rubber stoppers down here, if you move that same defect up here, you're assuming the system makes the same defects across the entire product. If that assumption holds true, or true to an engineering level of standpoint, then creating synthetic data actually does create some value um, uh, over actually trying to get all this data by real. So I think that's very um, a very important concept, is what are we actually creating with this data set, and are we overweighting something that doesn't really occur at what the system's going to do. And then finally, like we saw in the student's thesis, after they introduced the synthetic data, they actually ran it on the line and monitored its actual performance, and it actually performed quite well. But without that validation step, I would be extremely careful and thoughtful before people start introducing this idea in synthetic data. Although in the right conditions, it can be very helpful.
Cool. Thanks, John. Another AI large language model question here. Observation that we seem to have two paths in AI, things getting smaller with edge computing and things getting bigger with LLMs. I know I saw recently that an LLM query requires about 10 times the power as a Google query here. So there's some real intensity associated with these. Given that geographic processing units are expensive, the question is AI now only for the groups with the big checkbooks?
And again, I'm the next level that I'll stay in the world that where I see the value and understand that. So the first is there's a manufacturing operation floor. The next one is product and process development, i.e., how do I actually bring in new designs into the manufacturing floor? Because in most industries, particularly automotive industry, you have 3 years to make money off that car. And in year 4, year 5, your profits disappear. Parts of the first of all, to define what we mean by Gen AI is basically by taking some relatively simple descriptions, you can actually start to produce relatively sophisticated designs, right? That provide meet the customer's needs, right? Like speeding up an automobile design. A lot of those systems are already there; they're just not connected, right? So I think a huge part of what people are calling Gen I, we already have those systems that do, automated 3D CAD, CAM, et cetera, and so on. The slow part is the workflow, because someone designs something on Thursday and it sits on someone's desk till Tuesday, right? Or the engineers who designed it have the new blueprint for the design, and the people on the floor can't find it. So while the general question of who's going to get LLMs and where it's going to go is one, but I think when you're trying to run operations in manufacturing and maybe a high mix, low volume shop, thinking about your workflow for these product development steps is the way to go. And looking at where I actually do and don't need something like Gen I, right? When I simply just need a better designed workflow process that's cloud-based.
Great. Got a follow-up question on the two gap and how do you know when you're making progress here? To ask, how do you know that phase one is stable enough for phase two? And does it make sense to move to phase two if only one part of the organization is ready for it? Asked a different way, can you get one function too far ahead of the others? Or do you focus on getting the whole organization to phase one?
So as long as you can draw your bound, so organizations are different sizes from 200 people to 200,000. And I would put it this way, as long as you can draw a boundary, your system all has to move. But if I can draw a boundary around like one facility of 100 to 200 people in a company of 20 to 40,000 people, yes, you can just do it with that piece. But if you're trying to do level 2 across the company without doing level 1s at the local sites, I think you'll struggle, right? And the evidence has borne that out. Anyone who's ever gone through an ERP upgrade knows what I'm talking about and would avoid that at any cost, right? It's not worth the stress on anyone's health. Plus, it's just a better way. So any way that you can, this is where creativity comes in. You can draw the boundaries of a subsystem where you can actually drive improvement because it's semi-autonomous and use that to scale like the rest of the organization will look at it. That is fantastic. And in fact, one example, Eric, I worked in a brewery. And what the brewery did was I helped them basically you would call it AI, I would call it electronic workflow. We managed to reduce their changeover times by 80%, which ended up in producing 7% more cases of beer, right? And the point was, this was one out of their 30 plus breweries across the world. And then the plant manager said, I felt like the Pope. Because once I actually did it in my brewery, everyone from all over the world came to see us. So if you can draw a boundary around a subsystem, drive that to success, that would be the high success, low stress path.
Got it. Great. Got a couple of questions about processes where produced materials can get lost or misplaced. And maybe this would be a good point to talk a little bit about observability role in Industry 4.0. Again, just to double click on that and what you see particularly in manufacturing processes.
Okay. So the former head of AWS, their IoT division, Dirk Discascalou, said the IoT is really about knowing where everything is all the time. So that's about knowing where it is and where it's moving. Now, one of the things is when you're running a manufacturing operations, you always have to be conscious of, is the money we're spending producing value for the customer? Because if you don't have it, knowing where everything is all the time costs money, right? So, just so we all know, I came to the Toyota production system as a control systems engineer. The genius that they actually established their boundaries and basically keep very little inventory. Not only does it reduce your lead time to serve the customer, if I don't have it, I can't lose it. So before we start putting tags on everything so that we know have perfect traceability of everything that's in our building, make sure that we have as little in that space as possible. I like to think of it as an operating room. If there is the wrong surgical tool in that operating room, it will get used improperly, right? So first, gain control over what's actually in the space. Then you can start thinking about tagging the critical equipment to make sure it is and where it's at. And in terms of visibility, I know this might sound shocking. One of my thesis students, did a pretty advanced MRP system into the company, which took about 9 months. Her first 2 months was putting all the the special die pieces into clear plastic boxes, so the frontline leaders didn't spend 3 hours looking for a new die set, right? So just a classic example of spend the extra time on how do we clean the system out before we spend money.
Terrific. John, I think we have time for one more question as before we wrap up. We had a question here about what's your perspective on whether AI reduces the possibility of innovation.
So, again, I'll give my perspective. I think people use AI and stop thinking about fixing problems, right? Because when you start talking about AI, you'll notice it's already become of a scale where we're not going to discuss that at the factory floor. That has to be discussed at the top level of the organization, right? And if you'll notice, now we're actually losing our capability to define problems clearly, to work with engage with the people who've actually done it, and we're simply buying technologies. And I have an excellent example from how Toyota's expert Obasan. He said our engineers have turned into vendor selectors, right? And I think the AI world could suffer from the same disease as he saw back in 2005.
Got it. Okay, John, thank you so much. Thanks to everybody who joined us today. Just want to put up one final slide here. We talked about, again, the Industry 4.0 program is going to be running on October 31st and November 1st in person. There's a QR code here to register for the program. Also, we didn't talk much about today, but you have a second program that you're teaching with Professor Retzef Levy of the Sloan School on building organizational resilience and a systems approach to managing risk and uncertainty. And you can scan for some information there on that as well. Great as always talking with you, and look forward to the upcoming programs. And Elaine, any final words?
Nope, that's it. Thank you so much for joining us, and we'll have the recording of this webinar out later this week, so keep an eye on your emails for that.
Super. Thanks,
Great.
everyone.
Thank you, everyone, and thanks for your time, and would love to hear your thoughts. Thanks again.